the density of states measure is going to be the convolution of density of states measures. And since we know a lot about one-dimensional case, we can deduce something about multidimensional case, and at least that gives a hint on what should we expect in multidimensional case in other models as well. So let me remind the definition of integrated density of states for one-dimensional system. So I remind that we consider discrete Schrödinger operator on the one-dimensional lattice on Z. And what you do, you take the finite interval, you restrict your operator on that finite interval, you equip it with Dirichlet boundary conditions, and then you consider that finite dimensional operator. You take the spectrum is a finite number of eigenvalues, you put the probability measure equidistributed on those eigenvalues, and then you give you do that construction for larger and larger finite dimensional approximations. What happens? The sequence of those atomic probability measures will weakly converge to some probability measure, and that measure is called density of states measure, and its distribution function is called integrated density of states. So this is what happens in one-dimensional case, and natural question is, can we generalize that construction for multidimensional case? The answer is yes, and the convergence is there, but you have to give the setting first. There are different ways to give the setting in multidimensional case. One of them is using tilings that we used before. Another one, even more general in a sense, is using so-called Delaunay sets. So let me use this one because that's the language that was used by Daniel Lenz and Peter Stallman recently for the very last most general result in that direction. So the Delaunay set by definition is a set, closed set on, let's talk about the plane also, the definitions will be in arbitrary Euclidean space. You take a closed set that consists of isolated points, those points are isolated, which means that there is a neighborhood of each point that doesn't contain other points, and the size of that neighborhood should be uniform for all the points. So this set is uniformly discrete. On the other hand, we want that set to be without huge holes. So we want to have some radius r, such that if you take a disk, doesn't matter where, of radius r, you will necessarily find some points from that set in that disk. So that object is called Delaunay set, and in order to get an object which resembles somehow quasicrystals, we need some additional property, and that property will be called finite local complexity. Finite local complexity is the following thing. Suppose that you don't see the whole plane at the same time. At the same time, you can see only some window. So you have a window, maybe of a very large but finite size, and you move that window over that plane and see what kind of patterns you can encounter. Suppose that up to translation, you can encounter only finite number of patterns for each window. That means that you have finite local complexity for the Delaunay set. For example, if you take the set of vertices of Eppin-Rose tiling, then it will be Delaunay set with finite local complexity. Now, in order to introduce an analog of the discrete Schrödinger, ergodic discrete Schrödinger operators, we need to consider the set of all Delaunay sets of finite local complexity. And in order to consider them at the same time, we need to introduce some metric in the space of those sets. So the metric can be introduced in the following way. If we had compact sets, then the metric is quite natural. It's a Hausdorff metric. So you say that two sets are close to each other if epsilon close, if epsilon neighborhood of first set contains the second, and epsilon neighborhood of the second contains the first. Let's do exactly the same, but we will require that property to hold for intersections of those sets with a disk of very large radius, say of radius 1 over epsilon. And that gives you a set of neighborhoods that defines some topology. And actually, so two Delaunay sets are close to each other if there is a huge disk such that inside of the disk, the part of the set inside of the disk will be close to each other in the Hausdorff metric. And that topology is called natural topology, and it can be actually given by some metric. It's metrizable, which means that there are no pathologies that you observe in some other strange topological spaces. You can think about that as about metric space. And what is true about this metric space is, first of all translations are continuous. So if you take the Delaunay set and shift it, you will get a continuous map in the space of all Delaunay sets. And secondly, if you take the set of all Delaunay sets with this metric, you will get a compact set, which is nice. If you have what's the action on the set of Delaunay sets? You certainly want to consider the action by translations, but in multidimensional case, those translations form not the group of real numbers, but the group of shifts. It's RD, or on the plane R2. And so you have an action of R2 on the set of Delaunay sets. So it's possible that in that set, for that group of translations, you have some invariant compact subsets. For example, let's consider some Penrose tiling, given, for example, for kites and darts. And let's consider the orbit of that particular Penrose tiling under all possible shifts. You will still get, by Penrose tiling, now I mean the set of vertices of that Penrose tiling, that Delaunay set. And you consider the set of all possible shifts. And then you take the closure of that orbit with respect to that natural topology. You will get a subset in the space of all Delaunay sets, and that subset will contain exactly all Penrose tiling such that locally inside of some window you will get exactly the same patterns as for the initial Penrose tilings. But the structure of that orbit can be quite complicated, namely it will look like a solenoid, actually. So locally it will look like RD, or in two-dimensional case R2, multiplied by a counter set. Let's consider even easier example. Let's consider the tiling of the line by short and long intervals with respect to the Fibonacci sequence, Fibonacci substitution sequence. Then this construction will give you something that is topologically exactly the Smale-Williams solenoid. Okay, so that's the set of that's your phase space, the phase space of the Delaunay dynamical system. And now what you can, so the difficulty here is that if you shift Delaunay set, so what do you want to consider as a space where your operator is acting? That's a L2 space from the Delaunay set to R. So you consider real values functions on the points, on the vertices of the Delaunay set. But if you shift it, then you can get completely different space. That's a different formula. It's a different Hilbert space. Nevertheless, what you can do, you can define the family of self-adjoint bounded operators. For example, the major example that we want to consider is a Laplacian, such that for that family, we say that this family have finite range. It means that if you take, the operator is given by that infinite matrix. So any element of that matrix should depend only on the finite neighborhood of one point and finite neighborhood of another point. So once again, for the Laplacian on Penrose tiling, whatever that operator does depends on the point and the points that correspond are located in a small neighborhood of a given point. And if the points are far away, then there is no action relation between those 2 points. And finally, it turns out that. So finally, what do we want to do? We want to take such a family of operators, we want to take such a tiling and such a Delaunay set, and we want to take a big part of the Delaunay set and consider the restriction of our operator to that big part of the Delaunay set. And we want to say that in a sense, the spectra of those finite dimensional operators will converge to the measures that corresponds to eigenvalues of those operators converge to some measures that we want to call the density of states measure. But the problem here is that if in one-dimensional case the boundary consisted of only 2 points, and we had reasonable hope that behavior of that matrix in those 2 points will not influence too much the eigenvalues, in our case the boundary can be huge. So what we want to introduce a special set of sets that we want to consider, namely we want the boundary to be small comparing to the set itself. And if you have a sequence of such sets, which is called Van Hoff sequence, then actually in this case you can formally prove that indeed you will get a convergence of those measures distributed on eigenvalues. That convergence will be nice. Convergence of the distribution functions will be actually uniform, and you can define the density of states measure for that multidimensional case. So this is a very general statement indeed, but in our case, let's just think about Penrose tiling. For Penrose tiling, the Laplacian can be calculated using just huge, say, squares. You restrict yourself into the points on that squares, you calculate the Laplacian, you equip all the points that you eliminate, you just put zeros there, you have a Dirichlet boundary condition, and those calculations, that's rigorous statement that claims that those calculations will lead to the right result. In one-dimensional case, we claim that density of states, integrated density of states is a continuous function. In multidimensional case, in general, this is not true. You may have some discontinuities, but Lenz and Stallman proved that all those discontinuities are necessarily given to you by the following construction. In two-dimensional case, for example, there are such graphs that with Dirichlet boundary conditions that support an eigenfunction of Laplacian, which is quite an amazing feature. But if this is the case, then let's do the following. Let's take the Penrose tiling, and for each vertex of the Penrose tiling, instead of that vertex, we will insert that strange graph that supports the eigenvalue of the Laplacian. Then naturally, if you take a huge square, then you will have lots of different eigenvalues that correspond to those points where you inserted that graph, and that will give you accumulation point that will correspond to the jump in the integrated density of states. This is a very strange feature of multidimensional case, but it's known that this is the only way to produce eigenvalues. So if you factorize, in a sense, your Delaunay set, then you can get rid of all the jumps. Okay, so this was a multidimensional setting, and essentially this is the only thing which is known in multidimensional setting for multidimensional quasi-crystals. So the natural question is the following: can we find any system, even simple one, where we can actually prove something rigorously? Because numerical results are really strange. And let's cheat a little bit, and let's consider so-called separable potentials. Separable potentials are given in the following way. So consider a family of one-dimensional discrete Schrödinger operators. You have just, if you have d-dimensional model, then you consider d different one-dimensional Schrödinger operators. And then we will consider the discrete Schrödinger operator in d-dimensional Euclidean space on d-dimensional lattice in the following way. For each point of the d-dimensional lattice, the value of the potential will be just given by the sum of values of the potentials at the corresponding coordinates. And then you consider this discrete Schrödinger operators on ZD lattice. So this is a complete analog of the Laplacian. You just take a point and you take the sum of all the values nearby. And then you add the value at the given vertex multiplied by that value of the potential. So once again, you consider a family of one-dimensional operators, and you have some one-dimensional potentials. So you have some several bounded sequences. So for each point in d-dimensional lattice, this point has d coordinates. So what I'm doing, I'm taking the value of the potential here as the sum of potentials that correspond to the first coordinate, to the second coordinate, to the third coordinate, and so on. So this is a very special class of potentials, certainly. But what is nice about this particular separable potential is that the spectrum of that operator will be exactly the sum of spectra, and the density of states measure is exactly the convolution of density of states measures that corresponds to those one-dimensional potentials that we started with. And that gives a chance to study those operators in much more detailed way. So for example, let's consider square Fibonacci Hamiltonian. So we consider two-dimensional lattice, and we consider the potential which is a direct sum of one-dimensional Fibonacci substitution potentials. Then exactly this model was studied by physicists in many different papers, mostly numerically, and they had very strange results. In particular, they observed that if coupling constant is small, then the spectrum looks like a counter set. It looks like there are no gaps at all, which was very surprising at the time because it was more or less accepted in the physical world already that quasi-crystals are characterized by singular continuous spectrum and gaps in the spectrum. But here you don't have any gaps at all. Let me show the results of numerical experiments. So those pictures were made by Mark Embry from Rice University. So this is the picture that I showed already. The horizontal line is a line of energies, the vertical line is a line of coupling constants, and for each fixed coupling constant, the horizontal line that intersects this set is exactly the counter set, which is the spectrum of the corresponding Fibonacci Hamiltonian corresponding to this particular value of the coupling constant. Now, what I want to take the sum of those spectra. So for each value of coupling constant, I take this counter set and take the sum of that counter set with itself. And I want to see what will happen. This is what will happen. For small values, you will get an interval. Then some gaps will start opening. For large values of coupling constant, it looks like you get a counter set again, and it's really not clear what's going on in between. So that's the picture. And this is, in a sense, a typical picture. For other models, for Schrödinger, for Laplacian on the Penrose tiling, the pictures are kind of similar as well. So that shows that it's a nice model. It explains what happens in a multidimensional case. And if you take a cubic Fibonacci Hamiltonian, you take the sum of three spectra, you get a very similar picture, certainly, as well. So how to explain these pictures and what actually those pictures suggest? Here? Certainly, because if you have an interval at some moment, then if you add a counter set, which is not, which doesn't have too small. Exactly. In the talk by Gugu Moreira, he considered sums of counter sets. That's what we're going to do. We want to consider sums of counter sets. So that's a direct relation with what Gugu Moreira is doing. Yes. All right. So it's known that thickness is a key characteristic of a counter set when you want to consider the sums of counter sets. So let me remind that the thickness is an phenom of all the ratios that you get when you remove intervals from a counter set. On each step, you take the ratio of the intervals that are on the right and on the left from the intervals that you removed. You divide it by the length of the interval that you removed, and you take the infimum over all those ratios. Thickness itself is really bad characteristic, bad in a sense that it behaves really unpleasantly with a counter set. For example, it's not a monotone. If you take a counter set with some thickness, sometimes it's possible to get a subset of that counter set that will have a larger thickness, and so on. So there are some really strange properties sometimes, but nevertheless, it's extremely useful because of the following gap lemma. by Sheldon-Newhouse, gap lemma claims that if you have two counter sets such that the product of thicknesses is larger than 1, actually larger or equal than 1, then either those sets are far away from each other in the sense that they are just far away from each other, or one of them is entirely in the gap of another. But if they are interrelated, then this property implies that the intersection is non-empty. But what does it mean that the intersection is non-empty? If you shift one of the counter sets, they are still interrelated, and thicknesses do not change. And therefore, if you shift them, then the sum will be still non-zero. It certainly doesn't matter whether you consider. Let's consider the difference of those counter sets. If the difference contains 0, that exactly means that the intersection is non-empty. And if you can shift it and difference still contains 0, that means that the difference contains an interval of 0. And it doesn't really matter much whether you consider differences of counter sets of sum or sums of counter sets. So this implies that if you have two counter sets such that the product of thicknesses is larger than 1, then the sum necessarily contains an interval. And moreover, if you take one counter set of thickness larger than 1, then the sum of this counter set with itself is an interval. For example, let's take a standard counter set. The standard counter set has thickness equal to 1, and let's prove formally that the sum of the standard counter set with itself is an interval from 0 to 2. Here is a nice proof. Let's construct a standard counter set not only on the interval 0, 1 in x coordinate, but also in y coordinate. And let's take the product of all the sets that we get in the construction on each step. So what we want to prove that some point A on the interval 0, 2 belongs to the sum of counter sets. Let's consider the line y is equal to A minus x, like this. If A is between 0 and 2, it means that this line is between this line and this line. So it must intersect at least one of those four squares on the first step. Well, exactly because of the same reason, it must intersect one of the smaller squares, it must intersect one of the smaller squares, and so on. So finally, just taking the nested sequence of those squares that you obtain, you get a point that belongs, on the one hand, to this line, and on the other hand, to the product of counter sets, which means that there are points x in the counter set and y in the counter set such that x plus y is equal to a. But that exactly means that a belongs to the sum of counter sets. Notice that this proof also shows that thickness equal to 1 is crucial, because if you take thickness a little bit smaller, which means that you remove on each step, you remove not 1/3, but a little bit larger interval, then it will be possible for this line to come like this and not to intersect any of those squares. And then the sum of those two middle alpha counter sets with alpha smaller than 1/3 will be a counter set. On the other hand, if you remove a little bit smaller interval, not 1/3 but smaller on each step, then the same argument shows that the sum is still going to be an interval. So thickness equal to 1 is actually crucial. So why is it important? It was used by Sheldon-Newhouse to show that there are persistent tangencies in smooth diffeomorphisms of a surfaces. So you take a horseshoe which is thick enough, so the thickness of the counter set which you obtain by intersecting of transversal with the stable foliation is going to be larger than 1, is going to be large, and the thickness for the unstable foliation is larger than 1, and then you assume that you have intersection at some point. Then by a small perturbation of a system, roughly speaking, what you do, you are trying to get rid of the intersection of two counter sets, and if the thickness is large, you just cannot do that. This implies that you can get stable intersections, stable intersection of those counter sets, which implies for that picture that you have persistent tangencies. You cannot get rid of those tangencies. And each tangency produces, by a small perturbation, produces attracting periodic point, and standard genericity arguments imply that in this way you can construct an open set in the space of diffeomorphisms where infinitely many attractors exist at the same time. Another application comes from number theory. Let's consider point between 0 and 1, and let's consider the continuous fraction expansion of that point. Let's try to ask the following question. How many points we can write down in such a way that continuous fraction expansion contains only digits only numbers from 1 to m, but not more than m. So let's denote the set of those points by f of m. And then, and that's what's shown by Hull in 47, then it turns out that any number can be represented as a sum of those two numbers from F4. So it turns out that this set, F4, or actually Fm for any m, is going to be a counter set. And that counter set is going to be dynamically defined in some sense. And the thickness, if m is large enough, for example, 4 is enough, then the thickness will be larger than 1. Well, he used actually these ideas, but he never used that word, and he never gave a formal definition. So I don't really know whether Neuhaus was aware of this work, probably not, but anyway, that's certainly a related issue. So, any two numbers can be represented as sums of any number can be represented as sum of two numbers where for continuous fraction expansion contains only digits 1, 2, 3, and 4. And that has some applications for some questions in number theory regarding the Lagrangian Markov spectra. Well, you can ask why F4, what about F3 or F2? People considered all those questions in all possible combinations. And it turns out that if you have, for example, a number, you can always represent it as a number from F2 plus number from F5, or a number from F3 and number from F4, and so on. Or as a sum of three numbers from F2, and so on and so forth. So more or less all the combinations were considered, and people have full classification of the results of this form. Yeah, that's exactly what they're doing. So people consider those dynamically defined counter sets. They estimate the thickness of those sets because those are explicit sets given to you by the Gauss map. And then you just apply the Neuhaus gap lemma. Sometimes it's not trivial. Sometimes it turns out that you can represent it as a sum, but you cannot represent it as a difference. That's the case when you have to use left-right thickness. So there are some details there, but essentially that's the same idea. You use thickness as the tool that allows you to prove that the sum of two counter sets contains an interval. Right? Remember that we discussed last time that the spectrum of the Fibonacci Hamiltonian is a counter set with a thickness that goes to infinity as coupling constant goes to 0. Well, that immediately implies that the spectrum of the square Fibonacci Hamiltonian is necessarily an interval if you take coupling constant which is sufficiently small. And that explains this part of the picture. If coupling constant is small, then the sum of two counter sets is an interval. So here you go. Well, what about the case when coupling constant is large? When the coupling constant is large, well, first of all, what's the standard result? The standard lemma is that if you have two counter sets such that the sum of box counting dimensions is smaller than 1, then the sum of those two counter sets is necessarily a counter set, and box counting dimension is not greater than the sum of box counting dimensions. This is a simple result because what is a box counting dimension? You just cover the set in the most economical way by epsilon intervals, and then you count how many intervals you need, and then you see how fast that number goes to infinity as epsilon goes to 0. And then the rate of that convergence is actually of that limit is actually a box counting dimension. Now, if you take the sum of two counter sets, then how to cover the sum? You can take a cover of first one, you can take the cover of the second one, and then you can take the following intervals. Take any interval for the first cover, any interval for the second cover. The sum is going to be interval which is twice larger, And the number of intervals that we will get in this way will be the product of numbers of intervals. That immediately implies that inequality and the fact that Hausdorff dimension, and since if the box counting dimension of that sum is smaller than 1, then it's a counter set, you get the result. So this implies that if lambda is large enough, then the sum of spectra is also the counter set. And once again, that explains that upper part of the picture. If lambda is large enough, that intersection with the horizontal line must be counter set. But notice that here we needed the thickness to be larger than 1, and there we needed the Hausdorff dimension to be smaller than 1. And there is a gap between those two conditions. So what happens in that gap? It's not clear so far. It's known that for a generic pair of counter sets, if the sum of Hausdorff dimensions is larger than 1, then the sum of those two counter sets at least contains an interval. But condition that we need generic pair is important here because there are examples where you have nice regular counter sets, but nevertheless the sum of those counter sets is a counter set again, even if of positive measure. So it doesn't contain any intervals. So somehow we want to use the ideas of that result, but we cannot do that because genericity assumptions that made in the result by Mareri and Yukos is really something that is hard to verify for a given family. So for a given pair of counter sets, it's really not clear what to do. And the dimension of perturbations that they need to do is really huge. It's not enough to have one parameter family to say that inside of that family for generic set you have something. Nevertheless, there are some results where you can actually prove something for the one parameter family of sets. This is a theorem for Perez and Salamiak, and they used to work with Bernoulli convolutions, and the result comes from number theory, and that's why they use such a strange notation. But what's written here is actually exactly a family of affine counter sets, nothing else. So what's written here? We consider a family of affine counter sets with the contraction coefficients lambda, and we have finite number of contractions. In this case, we have m contractions, and that contraction, depending on lambda, may depend on lambda somehow. So that means that those coefficients may depend on lambda somehow. So you have a smooth family of affine counter sets, and you also want the images of the initial interval under the those contractions not to intersect each other. So that's exactly what they call strong separation condition, but in dynamical terms it's a completely trivial condition. You just want each of the contraction to send the whole counter set somewhere in such a way that the images do not intersect. And they proved that in this case, for almost all contraction parameters, if the sum of Hausdorff dimensions of those sets is smaller than 1, then the dimension of the sum is going to be the sum of Hausdorff dimensions, and hence must be a counter set. But if the sum of Hausdorff dimensions is larger than 1, then the sum of those counter sets must have positive Lebesgue measure. Moreover, they managed to replace one of the counter sets by arbitrary compact set. Just take any compact set K and change only the second counter set. That's still true. So that's inside of the one parameter family. You take any compact set. So in my case, I want to take K to be another counter set. But in general, you can take any compact set which is not completely trivial because you want Hausdorff dimension to be positive. Otherwise, there is nothing to consider. So you take any compact set of positive Hausdorff dimension, and you add to that compact set a counter set from that family. Well, sorry, that should be sub lambda certainly. So Then you consider that sum when your parameters varies. It turns out that for almost all parameters, if this condition is satisfied, you will get the sum, which is a set of positive Lebesgue measure. Okay. All right. So what should we expect? It turns out that it's totally impossible from the numerical experiments to understand what is there, because you have something that reminds you counter sets, there are lots of gaps, but at the same time somewhere else you may find some intervals, and it's not clear whether that's actually a small interval or just gaps are so small that you don't see that. It's really not something that you can see in the computer experiments. But now we can make conjecture. So conjecture is the following. First of all, let me remind what the counterval is. Guga Moreira mentioned those sets already. A compact set is called a counterval if it has dense interior, it has uncountably many connected components, and none of those connected components is isolated. So how should you think about it? Let's take a standard counter set, or just any counter set. Let's take a countable set of points which is dense in that counter set. And let's inflate each point from that countable subset, and instead of each point, you will glue in small interval. So small that the sum of all intervals that you glue there is going to be finite. So what you get will be a counter set with lots of intervals everywhere. So the interior is dense. It's certainly not a counter set anymore, but it's something that looks like a counter set anyway. So this is a counter interval. And the result by Moreira and Morales claims the following. Consider a smooth families of pairs of counter sets. And suppose that those counter sets are dynamically defined. And suppose that for zero value of the parameter, the sum of that should be zero. So for zero value of the parameter, the sum of the Hausdorff dimensions is equal to 1. And the sum of those Hausdorff dimensions changes nicely when you change parameters. So it's not stuck in one, it's growing. Then for generic family of that type, if you consider the sum of those two counter sets, then for small enough values of the parameter, but positive, so the sum of Hausdorff dimensions is already a little bit larger than 1, the sum is going to be counterval. Yes. So this. Yes. But no. There is no contradiction here because it's a counterval, so it does contain interval, but nevertheless it's not a finite union of intervals. It's a counterval. So, okay. And notice that this is exactly the setting that we have in the square Fibonacci Hamiltonian. So you have the sum of one-dimensional spectra. At some moment, the sum of Hausdorff dimensions becomes equal to 1. We know that Hausdorff dimension when lambda is large is really small. When Hausdorff dimension tends to 1 when lambda is small, so it monotonically changes. So somewhere it crosses. It becomes larger than 1 when you decrease the coupling constant. And at that moment, you would get countervals. Well, unfortunately, in this proof, the proof works only for residual set of families. And we have a very particular, very specific family, and there is no way we can make a perturbation. And so it's totally not clear whether for this particular family you have a counterval or not. Also, there is no reason to believe that that family is specific or degenerate in any case. It's not in any way. It's not degenerate at all. And so it's totally reasonable to make the following conjecture. So consider that picture that we've seen. And consider the sum of those two counter sets, those one-dimensional spectra, when lambda changes from 0 to infinity. Initially, the sum should be equal to the interval. Then at some point you may have some gaps appearing and you may get finite number of intervals for a while. Then at some moment that finite number of intervals becomes a counterval, And when you increase lambda even larger, then the Hausdorff dimension of that one-dimensional contraset becomes smaller than 1/2, so the Hausdorff dimension, the sum of Hausdorff dimension becomes smaller than 1, and then the sum of two one-dimensional spectra becomes a contraset. And that totally explains the picture, and the picture looks very reasonable now. No, that's exactly the point. This is a conjecture. Okay, this is a general statement. If you give me any compact set on the line, there exists a potential such that the discrete Schrödinger operator with that potential has a spectrum which is exactly this compact set. So there are such operators that the spectrum is a counterval. But it's not interesting at all because those operators do not correspond to any physical model. So in this case, there is a chance to get a natural potential that is a counterval, and that will be absolutely new phenomenon in the spectral theory because people don't know any physical models that would lead to countervals as examples. And it looks like it's essential, it's very natural here. It looks like that's what you have to expect for multidimensional quasicrystals for intermediate values of the coupling constants. But once again, that's just a conjecture. So what are the thresholds for those? What are those moments? It's natural to expect that you change from counterval to a contraset when Hausdorff dimension of one-dimensional spectra becomes equal to 1/2. And it's natural to expect that you change from finite number of intervals to counterval when local thickness becomes equal to 1. So local thickness is analog of thickness that you can define in the following way. Take a dynamically defined contraset. Take any point, take a small neighborhood. Consider the thickness of that neighborhood, of the contraset in that neighborhood, and take the limit. That will be local thickness at this point. For a dynamically defined contraset, local thickness doesn't depend on the point, and so that's a natural characteristic of the contraset itself. It can be strictly larger than the thickness of the contraset. Consider the following example. Take a standard contraset, and take another standard contraset, and take a contraset which is the union of those two standard contrasets with a huge gap between. The thickness of this guy is going to be small because of this huge gap on the very first step. But if you take local thickness, it's still equal to 1 because it doesn't depend on those finite number of gaps. All right. So, okay. We mentioned that the spectrum is a sum of spectra, and we also mentioned that the density of states measure is the convolution of density of states measures. And even if this sum of spectra is an interval, it's still not clear whether the density of states for that square Hamiltonian is absolutely continuous or not. Because the convolution of two singular measures could be absolutely continuous or it could be singular. And it's known to be a hard problem to distinguish between those two cases. So what is possible to prove, and this is a very recent result, maybe I should even put it as a preliminary version of the theorem. It's not written yet. But nevertheless, the result is the following. Consider a contraset that is unstable manifold of the horseshoe intersected with the horseshoe. So it's a horseshoe on its unstable manifold. And consider a measure on that contraset which is just unstable component of the measure of maximum entropy. And suppose that you have thick horseshoes, the local dimension is sufficiently close to 1. Then if you have a family of those horseshoes, which is non-degenerate family in a sense. Non-degenerate means that Lyapunov exponent with respect to the measure of maximum entropy should be changing. It shouldn't be standing at some point. It should have a derivative which is non-zero. Then for almost, so what I want to do, I want to take this measure of maximum entropy along the unstable manifold for one value of coupling constant and for one value of the parameter, and maybe this measure for another value of the parameter, and take the convolution. So for almost all pairs of parameters, I will get a convolution which is absolutely continuous. And this implies after some additional efforts. I formulated that only in the case of horseshoe, just because that's exactly the case of the trace map. I believe that it can be generalized essentially, but since I had exactly that application in mind, that's the way I formulated the theorem. I don't think that it's really important. All what is important is that Lyapunov exponent is changing, because what is important, you don't want to be stuck in a resonance. You don't want to be stuck in a resonance. So it's known that there are singular measures such that the convolution is also singular. For example, in the Erdős program for Bernoulli convolutions, there are some Pizot numbers where the corresponding Bernoulli convolution is singular. But you can get rid of it exactly because you are changing the parameter. So the parameter should be such that the scaling of the counterset that you consider is changing. So that's exactly what was used by Perez and Salamiak in that paper, where they consider affine countersets. But here we don't have affine countersets, we have some countersets. But we still want to say that the scaling is changing, and the right way to say that here is to say that Lyapunov exponent is changing. That means that for most points, the expansion rate is changing. Okay? All right. And as an application, for the square Fibonacci Hamiltonian, you can actually take one coupling constant along one component and another coupling constant along another component. So actually you have two parameter family. So for almost all pairs of the parameters that are small enough, the density of states measure of the square Fibonacci Hamiltonian is absolutely continuous. And let me stop here. I can't hear you. Yeah, absolutely. So you have convolution of several measures. If convolution of first two is absolutely continuous, then the convolution with the next one is necessarily absolutely continuous.